Hello friends, welcome to my lecture on sequences and series of complex functions. Let us consider an infinite series of functions of a complex variable. We shall see that most of the definitions and theorems obtained for infinite series of real terms can be applied with little or no change to the series whose terms are complex. Let us consider a sequence f and z n equal to 1, 2, 3 and so on be a sequence of functions defined on a set D of complex numbers. Then consider the series sigma n equal to 1 to infinity f n z equal to f1 z plus f2 z and so on f n z and so on. Then the sum of the first n terms of the series is given by the function s n z. S n z is equal to sigma m equal to 1 to n f m z, and it is called the nth partial sum of the series. The series is said to be convergent on the set D if limit n tends to infinity s n z is equal to f z exists for every z in D. The function f z is then called the sum of the series at the point z in the complex plane. By definition of limit, the series sigma m equal to 1 to infinity f m z equal to f1 z plus f2 z and so on f n z converges to f z if for a given epsilon greater than 0 we can find a positive integer n naught depending on epsilon and z such that mod of s n z minus f z is less than epsilon for all n greater than n naught. You can see that the definition is here is same as we have in the case of a series of functions of a real variable. Now, the function f n z here is called the general term or the nth term of the series sigma f m z, where m is equal to 1 to infinity. Now, from 3 it follows that, let us look at 3 from this inequality, it follows that mod of s n z minus f z means s n z is the sum of the first terms of this series. Okay, so s n z minus f z means you will have s n z minus f z equal to f n plus 1 z plus f n plus 2 z and so on. First n terms from the some function f z will be removed and we will have the terms f n plus 1 z and so on f n plus 2 z and so on, which we denote by r n z. R n z is called the remainder of the series after n terms. So, mod of r n z is equal to mod of f n plus 1 z plus f n plus 2 z and so on modulus of this quantity, that is this must go to 0 as n goes to infinity. Mod of we can see mod of s n z minus f z, this is equal to mod of sigma m equal to 1 to infinity f m z minus sigma m equal to 1 to this is n, here m equal to 1 to infinity f m z. So, this is equal to mod of f n plus 1 z, f n plus 2 z and so on and so on. Okay. So, mod of r n z minus f z is said to be the sum remainder after n terms of the series and we denote it by r n z. So, r n z mod of r n z is equal to this. This should be less than epsilon for all n greater than or equal to n naught depending on epsilon and z, and this means that mod of r n z should go to 0 as n goes to infinity. R n z is called the remainder of the series after n terms. Now, if limit in 2 this is your 2, okay. If limit in 2 exists, if the limit in 2 does not exist for some z equal to z naught, then we say that the series is divergent at z equal to z naught, and if this occurs for every z in D, that is the series is divergent for every z in D, we call it a divergent series in D. Now, the series 1 is called absolutely convergent, we call this series 1 to be absolutely convergent if the corresponding series of absolute values of the sequence functions f n f m z is convergent. So, mod of sigma m equal to 1 to infinity mod of f m z, if it is convergent, we say that the given series is absolutely convergent at the point z. Now, this series given by equation 1, this series is called conditionally convergent if it is convergent but not absolutely convergent. Since the series sigma n equal to 1 to infinity mod of f n z is a series of positive real terms, okay, the criteria for convergence for a series of real positive terms can be applied to this series. So, if sigma n equal to 1 to infinity f n z is absolutely convergent, it means that sigma n equal to 1 to infinity mod of f n z, this is a convergent series, okay, and therefore the remainder after n terms of this series R n z will be mod of f n plus 1 z, mod of f n plus 2 z and so on. So, this if this series is convergent, then the remainder after n terms of this series R n z must go to 0 as n goes to infinity. So, when R n z goes to 0 as n goes to infinity and R n z consists of the absolute values of f n plus 1 z, f n plus 2 z and so on, then it follows that f n plus 1 z, f n plus 2 z and so on, that also goes to 0, because mod of f n plus 1 z, mod of f n plus 1 z plus f n plus 2 z and so on. Okay. So, when f n plus 1 z, mod of f n plus 1 z, mod of f n plus 2 z and so on goes to 0, then this will also go to 0. Okay. So, we will have sigma n equal to 1 to infinity f n z is convergent, and therefore, absolute convergence implies convergence, but the converse is not true. We shall see an example on this fact. For example, let us consider the series sigma n equal to 1 to infinity minus 1 to the power n minus 1 z to the power n over n. We can see that this series is convergent for z equal to 1, because at z equal to 1 we get sigma n equal to 1 to infinity minus 1 to the power n minus 1 divided by n, which is 1 minus 1 by 2 plus 1 by 3 and so on, which is an alternating series, and by Leibniz real test we know that this series is convergent. It is convergent. Okay. So, at z equal to 1 this series is convergent, but if you take the absolute value of each term, that is you consider sigma n equal to 1 to infinity mod of minus 1 to the power n minus 1 z to the power n divided by n. Okay. Then you get sigma n equal to 1 to infinity z to the power n mod of z to the power n divided by n, and at z equal to 1 this series is harmonic series sigma 1 by n, n equal to 1 to infinity, which is known to be a divergent series. And therefore, at z equal to 1 this series is conditionally convergent. Okay. So, at z equal to 1 the given series is convergent, but not absolutely convergent. So, it is the given series is conditionally convergent. So, this series is convergent, but does not converge absolutely for z equal to 1. Now, the terms of an absolutely convergent series can be arranged in any order, and all such rearranged series converge to the same sum. Further, the sum, difference and product of absolutely convergent series is convergent. Now, these results are not true in the case of a conditionally convergent series. Now, Cauchy's criterion, convergence criterion holds for series of complex numbers. So, a necessary and sufficient condition for the series sigma n equal to 1 to infinity f n z to be convergent is that for a given epsilon greater than 0 we can find a positive integer n naught such that mod of s n plus p z minus s n z is less than epsilon for all n greater than n naught and for every p equal to 1, 2 and so on. Now, if you put p equal to 1 here, then mod of s n plus 1 z minus s n z is equal to mod of f n z, because s n plus 1 z is the sum of the first n plus 1 terms of this series and s n z is the sum of the first n terms of this series. So, mod of s n plus 1 z minus s n z will be equal to mod of f n z, and this is less than epsilon for all n greater than n naught. So, this means that f n z must tend to 0 as n goes to infinity. So, a necessary condition for the convergence of the series sigma n equal to 1 to infinity f n z is that the nth term of the series must go to 0 as n goes to infinity, but this condition is not sufficient. Let us take an example on this. You can consider again the series sigma n equal to 1 to infinity minus 1 to the power n minus 1 z to the power n minus 1 over n. At z equal to minus 1 we can see sigma the series becomes at z equal to minus 1 we get sigma n equal to 1 to infinity minus 1 to the power n minus 1 into minus 1 to the power n minus 1. So, minus 1 to the power 2 times n minus 1 divided by n, okay, which is equal to sigma n equal to 1 to infinity 1 by n. And so, the nth term of the series f n z was the nth term of the series. F n z was equal to minus 1 to the power n minus 1 z to the power n minus 1 divided by n, and this gives us f n minus 1 equal to 1 by n, which goes to 0 as n goes to infinity. So, nth term of the series goes to 0 as n goes to infinity, but what we notice is that if you put n equal to minus 1 in the series is sigma n equal to 1 to infinity f n minus 1 is equal to sigma 1 by n, which is a divergent series. So, the series satisfies the necessary condition for convergence, that is nth term of the series goes to 0 as n goes to infinity, but the series is not convergent. So, it is just the necessary condition for the convergence of the series, it is not sufficient. Now, let us consider, let u n x y and b n x y be respectively the real and imaginary parts of the function f n z. F n z is equal to, let us assume that f n z is equal to u n x y plus I b n x y for all n equal to 1, 2, 3 and so on. So, u n z and b n u n x y and b n x y are real and imaginary parts of the function f n z of the complex variable z. Then for any fixed z, the series sigma f n z is equal to f 1 z plus f 2 z and so on converges to the function f, whose real part is say u x y, imaginary part is b x y, if and only if the series of real parts sigma u n x y, that is u 1 x y plus u 2 x y and so on, and sigma b n x y, which is b 1 x y plus b 2 x y and so on, converge to the sums u x y and b x y respectively. Now, of all the tests for the convergence of a series of real terms, the ratio test and the root test are, we know they are the most important ones. For a series of complex functions, they are as follows. So, let n go to infinity, limit n tends to infinity, mod of f n plus 1 z over f n z is equal to mod of r z. Then the series sigma n equal to 1 to infinity, f n z converges absolutely for those values of z for which 0 is less than or equal to mod of r z less than 1, and diverges for those values of z for which mod of r z is greater than 1. The test fails for those values of z for which mod of r z is equal to 1. So, let us consider the series sigma n equal to 1 to infinity minus 1 to the power n minus 1 z to the power n over n. Then here f n z is equal to minus 1 to the power n minus 1 z to the power n divided by n, and therefore, if you find mod of f n plus 1 z over f n z, it comes out to be minus 1 to the power n z to the power n plus 1 divided by n plus 1 into n over minus 1 to the power n minus 1 into z to the power n, and this is equal to n over n plus 1 mod of z to the power n plus 1 over mod of z to the power n. So, we get mod of z, and therefore, limit n tends to infinity mod of f n plus 1 z over f n z is equal to limit n tends to infinity n over n plus 1 into mod of z. N over n plus 1 as n goes to infinity tends to 1. So, we get mod of z, and thus R z here is equal to mod of z, and so we can say that the given series converges absolutely, the given series converges absolutely if mod of z is less than 1, diverges if mod of z greater than 1. The test fails if mod of z equal to 1. Okay. So, we have to see what happens in the case mod z equal to 1 separately. So, the series converges absolutely for mod z less than 1, diverges for mod z greater than 1. However, when mod of z equal to 1, the test fails, and why it fails we can see that at z equal to 1, let us look at z equal to 1, what happens. Z equal to 1, the series becomes sigma n equal to 1 to infinity minus 1 to the power n minus 1 over n. You can see this is what we get at z equal to 1, and this series is what 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. So, that is a convergent series by Leibniz real test. Okay. So, this is convergent at z equal to 1, and at z equal to minus 1, if you find this series at z equal to minus 1, what will happen, sigma n equal to 1 to infinity minus 1 to the power n minus 1 into minus 1 to the power n, we will get this series sigma n equal to 1 to infinity minus 1 to the power n minus 1 into minus 1 to the power n divided by n, and this will be equal to minus sigma n equal to 1 to infinity 1 upon n. Okay. Or we can say we will get this series. Okay. Sigma n equal to 1 to infinity minus 1 by n, and this series we know this series is divergent because sigma 1 by n is a divergent series. Okay. So, we can say that at whenever mod of z equal to 1 here, okay, we cannot conclude about the convergence or divergence of the series. Now, let us consider root test for the series of complex functions. So, if limit n tends to infinity mod of f n z to the power 1 by n is equal to mod of s z, then the series sigma n equal to 1 to infinity f n z converges absolutely for all those values of z for which 0 is less than or equal to mod of s z less than 1, and diverges for those values of z for which mod of s z is greater than 1. The test fails for those values of z for which mod of s z is equal to 1. Let us test the convergence of this series. We are going to consider an example of a series sigma n equal to series of complex functions sigma n equal to 1 to infinity 1 by n square z minus 1 over z plus 1 to the power n minus 1, and we can apply here ratio test. So, when you apply ratio test, what we get, mod of f n plus 1 z over f n z, let us find, this is equal to mod of 1 over n plus 1 square z minus 1 to the power n divided by z plus 1 to the power n, and this is f n plus 1 z and divided by f n z. So, n square z minus 1 to the power n minus 1 and z plus 1 to the power n minus 1. Okay. So, this will be equal to n square divided by n plus 1 whole square, and we will get here mod of z minus 1 divided by z plus 1. Okay. So, limit of this ratio. Okay. So, limit n tends to infinity mod of Fn plus 1 z over Fn z will be equal to limit n tends to infinity n over n plus 1 whole square into mod of z minus 1 over z plus 1. Okay. So, this is equal to n over n plus 1 goes to 1. So, this is equal to mod of z minus 1 over z plus 1, and therefore, we can say that when mod of z minus 1 over z plus 1 is less than 1, the given series converges absolutely, and when mod of z minus 1 over z plus 1 is greater than 1, the given series diverges. Okay. When mod of z minus 1 over z plus 1 is equal to 1, we shall have to see what the nature of the series separately. So, hence the series converges absolutely for those values of z for which mod of z minus 1 is less than z plus 1. Now, let us see what are the points z where these points are located. Mod of z minus 1 is the distance of z from the point 1. So, z equal to 1 is here and z equal to minus 1 is here. Now, this inequality is valid for all those z whose distance from 1 is less than the distance from minus 1. Okay. So, this means that all the points which lie to the right half of the z plane, okay, the distance of this z from minus 1 will always be greater than its distance from 1. Okay. So, this means mod of z minus 1 less than mod of z plus 1 means real part of z greater than 0. Okay. So, this inequality tells us that the values of z which lie to the right half of the z plane. Right half of the z plane means x for which x is greater than 0. We can do it analytically also. Here we have done it geometrically. We can do it analytically also. So, let us, if we want to do analytically, let us put, let z be equal to x plus iy. Okay, then mod of z minus 1 less than mod of z plus 1 implies that under root x minus 1 whole square plus y square is less than square root x plus 1 whole square plus y square. Squaring both sides, we get x minus 1 whole square plus y square less than x plus 1 whole square plus y square. This y square and this y square cancel. You can now open this. So, we have x square minus 2x plus 1 less than x square plus 2x plus 1. We can cancel 1 x square and then what we get 4x greater than 0. So, which implies that, so x greater than 0 means that we the points which lie to the right half of the z plane satisfy the inequality mod of z minus 1 less than mod of z plus 1, and the series diverges for values of z for which mod of z minus 1 is greater than mod of z plus 1, that means left half of the z plane. So, that means x greater than 0 for values of z which lie to the left half of the z plane, that means the values of z for which x is less than 0. Now, test fails for the values of z for which mod of z minus 1 equal to mod of z plus 1. Mod of z minus 1 equal to mod of z plus 1 means x equal to 0. Okay. If you put here instead of less equality, then we will have 4x equal to 0. So, x equal to 0. So, mod of z minus 1 is equal to mod of z plus 1 means the points in the z plane whose distance from 1 and minus 1 are same. So, that is the points which lie to on the imaginary axis. Okay. Any point on the imaginary axis has its distance from 1 and minus 1 same. Okay. So, for values of z which lie on the imaginary axis, for points on the imaginary axis the corresponding series of absolute value is, now let us see what happens. So, if you take modulus here, okay, sigma n equal to 1 to, let us consider the series of absolute values, sigma n equal to 1 to infinity 1 by n square mod of z minus 1 upon z plus 1 raised to the power n minus 1. Okay. So, now when mod of z minus 1 upon z plus 1 is equal to 1. Okay. we get sigma 1 by n square series, okay, which we know is a convergent series. So, when mod of z minus 1 over mod of z minus 1 over z plus 1 is equal to 1, okay, we see that the series is convergent, and therefore, the series is absolutely convergent for values of z which satisfy mod of z minus 1 less than or equal to mod z plus 1, and for mod of z minus 1 greater than mod of z plus 1, the series is divergent. Okay. So, the series converges absolutely for real part of z greater than or equal to 0, that is x greater than or equal to 0. For x greater than 0, we find from here, okay. For x equal to 0, we have seen separately that the series is absolutely convergent and diverges for x less than 0. Now, let us consider the series sigma n equal to 1 to infinity n minus 1 over n to the power n, okay, z over z plus 1 to the power n. So, here when we apply root test, then limit n tends to infinity mod of f n z to the power 1 by n. When you take 1 by n as root of this f n z, we get mod of f n z raised to the power 1 by n equal to n minus 1 by n into z over z plus 1. As you know, this root test we apply when the nth term of the series contains n in the exponent. Okay. So, here we have n in the exponent of n minus 1 by n, and therefore, it will be convenient to apply a root test. So, this is what we have. Now, then limit n tends to infinity, if you find n minus 1 over n goes to 1 as n goes to infinity. So, we get mod of z over z plus 1, okay, and therefore, the series converges absolutely for values of z for which mod of z over z plus 1 is less than 1. So, absolute convergence for mod of z less than mod of z plus 1, and divergence for mod of z greater than mod of z plus 1. The test fails for mod of z over z plus 1 equal to 1. Okay. The test fails for this. So, mod of z less than mod of z plus 1 means what? It is the set of those points z whose distance from 0 is less than the distance from minus 1. Okay. And if you take this is 0 here and minus 1 here. Okay. So, distance from minus 1 is less than this distance from 0. Okay. So, this is minus half. Okay. This minus half. So, this means that if you take a point to the left of this is x equal to minus half. If you take a point left to the left of x equal to minus 1, its distance from minus 1 will be less than its distance from this. Okay. So, this means that we take the right half of this x equal to minus half. If you take the right half, then distance of a point from minus 1 will be more than the distance from 0. So, this actually tells us it is real part of z greater than minus half. We can see it also directly, z is equal to x plus I y will give you square root x square plus mod of z less than mod of z plus 1. If you want to see analytically, we can write under root x square plus y square for mod of z, and here we can write under root x plus 1 whole square plus y square. So, squaring we have x square plus y square less than x square plus y square plus 2x plus 1. So, these two cancel and we get 2x plus 1 greater than 0 or x greater than minus half. So, right half of right side of the line x equal to minus half, okay, this part. Okay. So, all points z must lie to the right side of x equal to minus half, and similarly when mod of z is less than mod of z plus 1, that is real part of z is less than minus half. Okay. So, this side, okay, for all any z to the left of x equal to minus half, the series is divergent, and the series test fails when mod of z over mod of z plus 1 is equal to 1. So, test fails for points z which lie on the line x equal to minus half. Now, the test fails for this. Okay. So, the corresponding series of absolute value is what? Let us see. When mod of z over z plus 1 is equal to 1, we get the series sigma n equal to 1 to infinity n minus 1 divided by n to the power n. Okay. So, when you put n equal to 1, it is 0. When you put n equal to 2, it is n equal to 2 will give you 1 over 2 raised to the power 2. Okay. And n equal to 1 will give 0. So, this is what we have. 1 over this gives you 1 over 2 raised to the power 2, and then n equal to 3 will give you 2 to the power 3 divided by 3 to the power 3, and then 3 to the power 4 divided by 4 to the power 4, and so on. So, and we can see that n minus 1 over n, the nth term of the series, n minus 1 over n to the power n, we can write as 1 minus 1 upon n raised to the power n. Okay. And so, limit n tends to infinity, this is equal to e to the power minus 1, okay, which is not 0. Okay. This is not 0. So, nth term does not go to 0, and therefore, the series is not absolutely convergent. Okay. So, the series is not absolutely convergent for real part of z equal to minus half. It can be shown that it is divergent for real part of z equal to minus half. With this, I would like to end my lecture. Thank you very much for your attention.